So welcome back. Our next topic we're going to be looking at is gases. Right. So in these segments, we're going to be discussing the properties of gases. We'll be looking at gas pressure and then focusing on Boyle's law. From there, we'll look at Charles' law, Gay-Lussac's law. These are mathematical relationships between pressure, volume, temperature, and pressure. Then we'll take those three and we'll combine them to form what we call the combined gas law. And then we'll bring the subject of moles back into it and look at how we calculate moles of gases. And before we get into those, typically I like to approach partial pressures so we can look at what happens when we have a mixture of gases and how we handle that. So the first thing we're going to do is just look at the concepts, because you're going to be familiar with a lot of these concepts already. A lot of these concepts we see every day, and so a little easier sometimes for students to manage on these. And then we'll get into the math after you understand the concept. This way, hopefully, you'll already have an idea of what the answers should be for the math. There we go. I had to make some adjustments there. Try to get the camera situated here so that ceiling fan is not going to be distractive in the background there. So anyway, as I was saying, we're going to look at how gases behave conceptually, then we'll go back and apply the math to it. So the gas laws in general then simply describe how gases are going to behave, which means we can predict them by theory. So we can kind of figure out how the pressure is going to change, how the volume might change, how the temperature might change, and then what those changes will do to the other aspects of the gases. So the amount of change then, what we can do is we can calculate this with mathematical equations. Now we'll be using algebra, so it's very similar to what we've been doing. Now I'll also remind you that before, every number I've given you, you've pretty much always needed to use in the calculations. Gas laws is where we start to introduce you to data that you won't actually use in the equation. So you got to be prepared for that part. All right, so conceptually then, what is the effect of adding a gas? So if I take a balloon and I start to blow up that balloon, what I'm going to do is ask you to think of this in terms of molecules. So as I breathe into a balloon, I'm pushing my CO2, my unused oxygen, and of course nitrogen that's just in my breath into the balloon, right? So the molecules are being forced into the balloon. And if I take another big inhale and then another big exhale into the balloon, what I'm essentially doing is doubling, tripling, quadrupling the gas particles that are captured by the balloon. Now, the pressure when that happens will also mathematically double, triple, or quadruple as long as the volume stays at the same, right? And the temperature stays the same. So if I'm blowing that balloon up at room temperature, the volume is obviously expanding. So the pressure won't be doubling as it is. But if you've ever taken like a 20-ounce water bottle and just kind of blown into it, you know that right away it wants to pop out of your mouth, right? And if you've never done that, you probably will now. And so you'll find out very quickly that when the volume can't expand as it is in a balloon, then that pressure goes up right away. So pressure and the number of molecules then are going to be directly related. Now, how does that relation work out? Well, the more molecules means more collisions, okay? And fewer molecules means fewer collisions. So the more molecules we have in there, the more collisions we have. Now, pressure, mathematically, is a force over an area. So if you think about it and you just sort of push on something, you can feel all of that force spread out over the area. But if you take your single finger and press with the same force, it'll hurt you a little bit more. And that's because now all that force is in a smaller area. So if I have lots of collisions taking place, then I'm going to have a bigger force that's hitting into that. Now gases will naturally want to move from high pressure to low pressure, right? So, and if you've ever done this experiment, you walk into a store, especially in the summer or going into fall when it's still warm outside, and these big stores have their air conditioners on, they usually have what they call back pressure. So when you open the doors, you feel a big gust of wind come out. And that's because the store is actually under pressure. They've been pumping air in that's cooled, and that air is going to come out now. All right, so if I double the number of molecules, what's going to happen? So here's my bicycle pump. So we've got the bicycle pump set up, and then I've got one ATM. Now, this is not an automated teller machine, right? So it's not the money machine. ATM is atmospheres. Okay, so this is one of our units of pressure. Okay, so atmospheres. This is one of the units we'll use, so you need to get familiar with atmospheres. The other ones that we'll use, millimeters of mercury. Okay, and there is a relationship here between millimeters of mercury and atmospheres. In fact, it's 760. I didn't give myself enough room to write there. Let's see if I can fix that real quick. So let's just erase that, and I'll go ahead and give you that conversion here. So we're going to have 760 millimeters of mercury equal to 1 atmosphere. Now, some other pressures units you might have heard of or you'll even see used are torr. Right? Most of us are familiar with PSI, pounds per square inch. So this is what we measure our tires on. So if you have a vehicle and you need to put air in the tires, typically a vehicle is anywhere between 35 and 55 PSI. And so when you go to Wawa for free air and you pump your tire up and you use a little tire gauge that's there, you're looking for PSI. There's also, I'm trying to think if there's any others that we'll run into. I don't think there are. There's several other units of pressure, just not ones we'll run into. All right, so as I pump molecules in, we can see the pressure goes up. So I gave one pump, I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 little molecules of gas, and I got 1 atmosphere of pressure. If I give a second pump, remember I'm going to double the pressure because the volume here in this canister is not changing. So now if I count it, I should have 20 molecules as well. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So now we've doubled the number of particles, and so we've doubled the pressure, right? And obviously if I keep pumping, I can get this thing up to 4 atmospheres. Now what I want to look at next is what happens when we start to remove molecules, or what happens if, I don't know, we just kick the little pin out of this thing and let the air just come flying out. So as we remove molecules, the container, obviously the pressure is going to decrease, right? And of course, if we put our hand right in front of here, we'd feel those little molecules smacking our hand, okay? That's the air pressure coming out. Now, how low will this thing go? That's the real key. So will it go down to 1 atmosphere, or will it keep going? Will it go lower? Will it go all the way down to 0? What happens? Well, now as I remove molecules, the pressure is going to decrease, and it's going to decrease until the pressure inside that canister equals the pressure outside of that canister. So if it was 1 atmosphere here, like here in Delaware, where I'm doing these things, we're at about sea level, which is about 1 atmosphere. So all that gas is going to come out to 1 atmosphere. If I lived in Denver, Colorado, then what's going to happen there? Well, even more is going to come out. It's going to be lower pressure there, right? Molecules will naturally move from high to low pressure. So if we have 2 systems and there's a pin in between them that's keeping them separated, once I remove that pin, the high pressure is going to bleed into the low pressure. Okay? Now, that's if the volume stays the same. What happens if I start messing with the volume? So in a smaller container, molecules have less room to move. Right? That's simple truth. You might not be able to tell this semester, or if you're not coming on campus, you can't tell. But on a typical Monday morning, our campus is just lively with cars, right? Cars are everywhere. And so the more cars we pack into the parking lot, the less room there is to move, right? Which means the molecules are going to hit the sides of the container more often. Now that's a relationship to pressure, right? So remember, as the volume decreases, then the pressure will increase. If I put more and more cars into the parking lot and somebody comes flying through, they're more likely to hit somebody else, right? Same thing here. The molecules are moving around, and if I have more of them, then they're more likely to hit the wall of the container, and then that would register into pressure, okay? If I take cars away, then of course there's less things to possibly run into. And so we'll see a decrease in the pressure. right? So as the volume decreases, the pressure increases. As the volume increases, the pressure decreases. So here's our first perfect canister. We call them the perfect canister or the perfect piston, because what's going to happen is this piece right here is free to move up and down. And we call them perfect because we're going to assume there's no friction. So the only forces that are acting on this are the molecules bumping into each other, and then of course the air pressure pushing down, right? So those are the only things that are affecting this. Now we're going to set this volume to be 4 liters, and then we're going to give it 1 arrow and 1 atmosphere of pressure. Now, as the pressure on the gas increases, what's going to happen? So you can think of this as, I'm going to push my hand down on this lid, and what's going to happen? Well, we would expect the lid would go down to some extent. Okay, so if I double the pressure, what I should see then is the volume cut in half. Okay, now again, that's in the perfect world. So that means it's 1-to-1 relationship. If I triple the pressure, I would expect the volume to cut to 1/3. If I quadruple the pressure, I would expect the volume to cut to 1/4. Now again, that's the perfect world. That's assuming there's no friction, there's nothing else going on, there's no interactions between the gas molecules. So we're making a lot of assumptions for this theory. Now, pressure and volume then are what we call inversely related, which simply means as one goes up, the other's got to come down. Okay? Now, the third thing that impacts our gases is going to be temperature. Raising the temperature of a gas will increase the pressure if the volume is held constant. Okay, now you've done this probably. If you've ever boiled water over in a pot, then you've seen this in action. So you take a pot, you put water in, and you start to boil it, and you get impatient, so you put a lid on it. And as you put a lid on it, the water itself starts to turn into gas. And so that means you're populating that. It's called a headspace. We're populating that headspace with more molecules, and the molecules trying to find space. They want to get out. And so eventually what happens is enough of them get in there, they cause enough pressure, and boom, the lid pops off, and then the pot boils over rapidly, right? The molecules here are going to be hitting the walls harder. So we got these little gas molecules. They have an X amount of energy, and they're moving around and they're hitting things. If I give them heat, we saw in chapter 2, well actually it was chapter 3, heat is a form of energy. So if I have a little toddler and he's already running all over the place and I give him a Pepsi, what's going to happen? Or a bag of chocolate, They're going to get even more wild and more crazy, and they're going to hit more things all over the place, right? It's going to be even harder to keep up with them. That's what we just did to these little gas molecules. They already had their own little energy. They're already moving around rapidly. I'm going to give them heat, which is going to force them to move around even more rapidly. And if they've got more speed and then they run into something, then they're going to hit it harder. And it's just the function of the way science is going to work. The only way to increase the temperature then at constant pressure is to increase the volume. Now, if we go back to that boiling pot of water, we see that water start to rapidly boil. And if we get there in time, we'll grab the lid, pull it off, and right away, the water just stops boiling. Goes right back to being bored. Now, why is that? Well, I just took that volume and I increased it to infinity, right? I mean, as far as that pot's concerned, we went from this little tiny headspace to your entire indoor home, okay? And if you got the windows and doors open, we just went to the entire atmosphere. All right, so let's take this into account and put this in our perfect piston one more time. Now you'll see at the top here I've got 300 K, so that's going to be Kelvin. Okay, so Kelvin temperature. What's Kelvin related to? Well, Kelvin is going to be equal to degrees C plus 273. So degrees C plus 273. Now, it's actually a little bit longer than that. It's like 273.15 and some more change, but all things considered, if you're adding 273, we're going to be in the ballpark every time, and it's going to be fine. Now, I'm going to start off in this perfect piston once again, but this time I'm going to have 1 liter of gas. I'm going to put it at 1 atmosphere, hence the 1 purple arrow, and we're going to start the temperature at 300 K. And now what I'm going to do is double that temperature. So I'm going to heat this canister up. Now, what's going to happen? And of course here, we know it's going to be one of 2 things, right? Either that perfect piston has to expand and let that gas have more space, or the pressure's got to double, right? So if I latch it here and I hook it so it can't move, then we're going to see the pressure has to double. Now in reality, if we tried this experiment, what we're going to see is someplace in the middle, right? So some of the gas is going to expand, and we're going to see an increase in the pressure at the same time. All right. Now, so far, in all these concepts of gases, what we've been talking about are ideal gases. And in this chapter, we're going to assume that all gases are going to behave ideally. Okay. Now, that's not true for reality. So what does this mean? So it does not really exist, but makes the math easier, and it's a close approximation. So the assumptions we're going to make is, number one, we're going to say particles have no volume. Now we know that can't be true, right? We have ammonia gas, we have chlorine gas, we have oxygen gas, we have hydrogen gas. There's no way those particles could all be the same size, let alone not take up any space at all, right? Just like the cars in the parking lot, different vehicles have different sizes. They take up more space than others. Same idea. The other thing we're going to assume is there are no attractive forces, and this is the one that really is way off base. All right, so if you ever have experienced static electricity, then you know that attractive forces exist by just two things passing each other. Right, that's all that's happening for static electricity. So if two things pass each other and can generate an attractive force, then obviously these gases that are moving everywhere can obviously generate some attractive forces. Now, there are no gases for which this is completely true. None. So no gas on the face of the earth behaves ideally on its own, right? No way. Real gases, however, can be forced to behave ideally at high temperature and low pressure. All right. So again, we're going to assume that all these gases are behaving ideally. And the reason why we're going to do that is it's going to make our math easier to handle. All right, so that's going to be segment one, all the concepts behind gases. And again, some of this stuff might seem like you already understand this, right? Because we've seen these things in practice. You may have taken a balloon, blown up that balloon and put it in the freezer, and you'll know that what's going to happen, right? Or, you've heated up that pot of water and you've seen that lid pop off. So gases affect us all around our world. And so a lot of times we'll see a lot of these things. We just don't have the math to put to it. And that's what we're going to do next. So in the following segments, we're going to start to put the math into what it is that we've observed most of our lives. All right, so stay tuned for the following segments.